Today I am going to start a new topic in that is red black trees. As we have gone through various kinds of tree in data structures also, and the DA is something which is enhancing the concepts which we have already studied in data structures. So for here we are going to study red black tree. Now what is a red black tree? It is basically a self-balancing binary search tree. The term associated here is the self-balancing binary search tree. Means in data structures we have studied binary search trees. What are binary search trees? Where parent lies between the left and right child. So here also the concept will remain same, but here we are inserting a new node, an extra bit that will represent the color. That color is either red or black. That is why it is known as red black tree. Now here are some of the properties of red black tree. That is, first property says that every node is colored either red or black. Means whatever binary search tree we are drawing here, in that tree the node is either red in color or black in color. Next is the root property. That means the root of the tree will always be black. Leaf property says that every leaf node is black in color. Here leaf node signifies the nil nodes. Means if I am drawing a tree like this, in general we say these are leaf nodes, but here leaf nodes are the nodes which do not have child, and further they are extended to the nil nodes. These are the nil nodes. So these nil nodes are black in color. Next, what is the red property? That if a red node has children, then the children are always black. Means a red node cannot have a red child. Next is the depth property, which is very important, that for each node the simple path, that is depth of any leaf node, is total number of black nodes are same. Means if I consider any path of this particular tree, number of black nodes will remain same in all the paths. That is the depth property. So this is one of the example of a red black tree. Here I have drawn the red black tree, in which you can see that all the nodes are fulfilling the property of binary search tree. That is, each and every parent node is lying between the value of left child and right child. Plus each and every node is either red in color or black in color. And this is the root node which is black in color. These all are the leaf nodes which are nil and will be black in color. Next, if there is a red node, it is having a children, then children are black in color. And here also these are the red nodes, and all the red nodes are the leaf nodes. That is 5, 7 and 15 are leaf nodes. So how can we say that these are having the black children? These null nodes. So the color of null node is black. So each and every leaf node is having 2 null child, that is black in color. Next we come to the depth property. So if I consider this particular path, so this is 1, 2 and null is 3. So total 3 black nodes are there. If I consider this path, again 1, 2 and 3, total 3 black nodes. If I consider this path, then 1, 2 and 3. Again, if I check this path, this is 1, 2 and this is 3. So if I go through any of the leaf node from root, the total number of black nodes are same in the midway. That is the depth property. So this is the example of red black tree. Now, in general we can say that all the two adjacent nodes cannot be red in color, as we have seen in this particular diagram also. That is, no two red nodes are adjacent, but black nodes can be adjacent to each other. So In this particular example, we are seeing also that the adjacent node to 4 is 3, that is black in color, and another node is 8, that is red in color. But for a red node, adjacent nodes must be black in color. They cannot be red because it says that red node cannot have red child. They can only have black child. Now, how red-black tree maintains self-balancing property? So, this self-balancing property is maintained by putting the limitations on the node colors, by ensuring that the simple path from each leaf node is not more than twice as long as another such path. So, by putting the restrictions based upon the colors, we ensure the self-balancing property. It helps the red-black tree to maintain its property, to retrieve all its properties which we have discussed earlier in these slides. Next, what are the basic operations on red-black tree? These are the insertion, deletion and search. These are generally the major operations which we can perform on any of the data structure. So here also we are going to perform the same insertion, deletion and search operation. So first we discuss the insertion operation, how to insert a node in a new in an empty red-black tree or in an existing red-black tree. So the insertion process is very much similar to the binary search tree. As we insert a new node in BST, in the same fashion we are going to insert a new node in the red-black tree, and the extra bit, that is the color of the new node inserted, is going to be red. So we have to keep in mind 2 points when we are going to insert a node in a red-black tree. First is the BST insertion, that we are going to follow the BST insertion, and second, whatever node we are going to insert must be red in color. So now there arises various cases. First case is whether your tree is empty or not. If your tree is empty, if in general I am not having any tree, means I am talking about the empty red-black tree, in that particular case, whatever node I want to insert is going to be the first node. So in that particular case, that node will become the root node, and root node of the red-black tree is always black in color. So in this particular case, the inserted node will become the root and it must be colored as black. Second case comes when your red-black tree is not empty. In that particular case, create a new node, color it with red and insert in the tree as we insert in BST. Here also there are 2 different cases. First case is if the parent of the new node is black, or second case is the parent of new node is red. So these 2 different cases will arise. For example, if I am saying I am having a tree 4, 3, 8. This is black, this is red and this is black. It is not a red-black tree, but I am taking an example that if this is the scenario, okay, complete it with a red-black tree only. Okay. Now, if I want to insert a node 1, so in that particular case, this is an existing RB tree, and if a new node is to be inserted 1, so it must be created first, and after that it must be colored as red. Now, what will happen? When I insert it in the red-black tree, 1 will be inserted to the left of 3. 1 will come here. So, which case is applied here? That a new node is inserted whose parent is black in color. Okay. Second case, if I want to insert Okay, let's discuss this case first. So, first case is clear, that is whatever parent color is, that is black. So, in this particular case, is any property of the RB tree is violating? No. We can check all the properties of red black tree. All properties are as it is. If any of the property is violating, then we will rotate it. But here there is no requirement of rotation. All properties are fulfilling. So when a new node, when the parent of new node is black, simply exit the operation and left the tree as it is. There is no requirement of any kind of change. Now, second case, if the parent of new node is red. Now, if I want to insert -1, what will happen? First case, I will create a new node, -1, which is red in color. Now, I will insert it in the tree. Now, what will happen? If I insert -1 in this particular tree, it will come to the left of 1. Now, see, the node, new node, that is red in color, is having parent which is also red in color. Okay. So, this is the second case when we perform insertion. So, what we will do in this particular case, because here the property of the red black tree has been violated, because in red, according to the red black tree property, there cannot be two adjacent red nodes. And here we are having two adjacent rows, that is 1 and -1. So what we will do here, we will do some shuffling or rotations and readjust the colors to balance the property. So if the parent of new node is red, then color and the color of parent sibling is either black, or if it does not exist, that means it is black only. Means if I say that this parent node is red in color and its sibling is not existing. So if there is no sibling, it means there is a nil node, and nil node is black in color. Means the sibling of parent node is black. Then we will apply the suitable rotation and recolor accordingly. Now what are the rotations here? Here we are having all the rotations which we have studied in AVL tree, that is LL rotation, RR rotation, RL rotation and LR rotation. So all the rotations are being performed here, but instead of balance factor, we will recolor the nodes. So if the parent of this new node is red and the color of the parent sibling is red, in that particular case, recolor the parent. So first case, it is clear, that is the parent is black and new inserted node is red in color. There is no need of performing any kind of change. Second case says when you are having parent red, whatever new node we are going to insert is red and its parent is also red in color. In that particular case, again two sub cases will arise, that the sibling of the parent is black or red. If parent sibling is black, in that particular case, rotations are required to be applied and recoloring is required. But if the parent sibling is red in color, in that particular case, only recoloring is required. We only recolor the nodes. We will discuss all the cases with the help of example in the next slide. So, these three, we can say these two major cases, and the second case with two sub cases is applied when we are going to insert a new node in a red black tree. Now let us take an example. So we have to create a RB tree that is having following nodes, and initially we are having a empty RB tree. So first node is inserted, created 1, and it will become a root node, so it is colored as black. Next, we have to insert 2. Now as per the BST property, for 2 is going to be inserted to the right of the 1. So your tree will become like this. Next is node 3. Now, when we insert 3 in the existing tree now, so the position for 3 is this, to the right of 2. So when we will insert this, you can see that the property of red black tree is violated because there are 2 adjacent red nodes. And what property is violating? Which case will be applied here? We can see here that new node is having red parent, means case number 2. And in case number 2, there are 2 sub cases, that is parent sibling is black or red. So here we can see that this is nil node and nil node is black in color. So parent's sibling is black in color. So case 1. So case 2 के अंदर आपको कौन सा केस लगाना है? Case A, which means that is we are going to perform any kind of rotation here. So which rotation will be applied here? You can see that rotation is RR rotation. So we are going to apply RR rotation. So after applying RR rotation, your tree will become like this. Now your tree will look this after applying RR rotation. So color is not changed here. The root will become 2 and 1 will come to the left child and 3 will become the right child, and the parent of the new node will become black in color. Next, all the properties are restored. We will insert 4. Now again, when we insert 4 here, what will happen? You can see the property has been violated. So in this particular case, again we have to rotate. So when we rotate, again see 4, the parent of 4 is red in color and its sibling is also red. So means case 2 B part. When parent is having red sibling, in that particular case we only recolor the parent and grandparent. So we will change the color of parent, that will become black, and we will change the color of grandparent, which will become red, but grandparent is root node, so it will again become black in color. So your tree will look like this. Parent and sibling are recolored to black from red, and grandparent will first convert it to red, but in this particular case, as grandparent is red root node, it is further converted to black color. Next, after inserting 5, we got this tree. Now check, the parent is red in color and its sibling is black in color, means rotation is required. Whenever sibling of parent is black, in that particular case rotation is required, and when parent sibling is red, only recoloring is required. So again here also RR rotation is applied. So after rotation we will get the tree. Next we have to insert 6. 6 is inserted to the right of 5 at this position. You can see parent sibling is red in color, so only recoloring is required, and after recoloring this will become black, this will become black, this will become red. Okay, like this. Since here 4 is not the root node, it will remain red in color. So this is the tree. Next we have to insert 7, which will be inserted to the right of 6. So after inserting 7, again we require rotation because sibling of 6 is black in color. So when parent sibling is black, we need to rotate the tree. So we will get this final tree as the answer. I hope the insertion concept is clear. Next, we come to the deletion operation. Now, for deletion also, again the concept will remain as it is of the BST. As per the BST, we will delete the node. There are two cases in BST also, that is node which we are going to delete is having 0 child or 1 child, or second is the node we are going to delete is having 2 children. So here also the same concept will be applied. So deletion, but after deletion also all the properties of red-black tree must be retained. So case 1 is if either the node to be deleted or the node's parent is red, just delete it. Means if we are going to delete a red colored node, just simply delete it. There is no need to perform any kind of operation further, because we are going to delete the red node, leaf red node, and that will not change the property of the RB tree. But if the node is a black node, leaf node is there, but that leaf node is black in color, we just simply remove that black node and the node will become double black, because we are not able to delete the color node. So simply a double black node will be created, which we have to further process by using various further cases to remove the double black property by removing that particular node by its predecessor node or the ancestor node. So case 3 says if the double black sibling node is also black node and its child are also black in color, then in this particular case, means your node is black, double black is black in color only. Now its child nodes are also black in color. In that particular case, simply remove the double black, recolor its parent to black, and if parent is also already a black, it will become double black. After that, recolor the parent sibling with red. Now, if double black still exists, repeat the process. Or if the process does not apply, we will go with the further cases. So further case says that if double black node sibling is red, means now double black node is existing but its sibling is red in color. In that particular case, we just swap the color of parent and parent sibling node and rotate parent node in the double black direction, and again further we apply the suitable cases. Next, case 5 says if the double black sibling is black node but the sibling child closest to the double black is red, means in this particular case the sibling of double black is black but the closest child to double black is red in color. In this particular case, we simply swap the colors of double black sibling and the sibling's child and rotate the sibling node in the opposite direction of the double black and again apply the next case. So after case 5, we only have case 6 which is to be applied if requirement exists. Okay. And what is case 6? That if double black sibling is a black node but sibling child node is farther from the double black. In that particular case, swap the colors of double black parent and sibling nodes, rotate the parent in double black's direction, remove double black and change the color of the red child to black. In the next lecture, we will discuss all the cases with the help of an example in detail. So, till then, you just go through all the properties and cases of the deletion of the red black tree. Okay. Now, if I take a little example of this, if I want to delete 4, 5 and 3. So here you can see that 4 is the node which is red in color and it is having child, 2 black child. In this particular case, binary search deletion is applied. So what is going to happen? 4 is deleted from its in order successor, that is 5. So 4 is replaced by 5. Now we have to delete 5 and 5 is a leaf node that is red in color. So we just simply remove 5. Next we have to delete 5. Now 5 is present over here with 2 child. So again 5 is replaced by its in order successor. So in order successor is 6. So 5 is replaced by 6 now. Now this is the situation. 5 is replaced by 6. Now 6 is to be deleted and 6 is having only one child, that is 7. So it is being deleted by 7. We have to retain the properties of BST as well as arbitrary. Next, we have to delete 6. In this particular case, one child is black and one child is red. So again, this 6 is deleted. It is replaced by in order successor, that is 7. Okay. But as soon as this 7 is deleted, it will create a double black node because it is black in color. As soon as we delete this 7, it will violate the property, black depth property of the arbitrary. So this particular situation will occur. This is your double black node. Okay. Now, how to search the data in the arbitrary? The concept is simple, that is with the, as we search data in the binary search tree, that is when first the data is compared with the root node, then we'll, as per the value of the data, we will look either in the left subtree or right subtree of the tree. If we talk about the time complexity of red-black tree, then binary search tree insertion and deletion takes log of n time in average case, and O of 1 is the best case and On is the average case. What are the applications? So red-black trees are useful in implementing finite maps. They are used in file systems, mapping, C++, kernels, various packages, or priority queues, graphics, game development. There are enormous uses of red-black tree where we can use the concept. So thank you for the patience listening. See you in the next lecture. Till then.